In this lesson, we'll examine the graphs of tangent, cotangent, secant, and cosecant. So let's begin with graphing tangent. So that is y is equal to tan x, like this. By definition, tangent is the ratio of sine to cosine. It's useful to think of tangent this way because it'll tell us what the domain of this function is. If cosine of x ever equals 0, we can't use that value in the tangent function. So just as a note off to the side, where is cosine of x equal to 0? Those are problem points. Those are values like plus or minus pi over 2. Pi is fine, but if you then go to plus or minus 3 pi over 2, plus or minus 5 pi over 2, and so on, all of these values make cosine 0, which means they're not in the domain of the tangent function. So what happens at these values? We have a vertical asymptote. And on the graph I have over here, well, I only have negative pi over 2 and pi over 2, but they do repeat at 3 pi over 2 and negative 3 pi over 2 and so on. So let me include vertical asymptotes here and here. Okay, so the next thing is, well, those are the vertical asymptotes. Those are not actually on the graph of tangent. What are some values that are on the tangent function? Well, if the numerator is ever equal to 0, then the entire function is equal to 0. So for example, where is sine of x equal to 0? This happens if x is equal to 0, plus or minus pi, plus or minus 2 pi, and so on. So let's see, if we're graphing tangent, it's equal to 0 at 0, as well as pi, negative pi, 2 pi, negative 2 pi, and so on. Maybe just to get two more values on this function so we have an idea of what this graph might look like, I think another important angle to consider will be pi over 4, which is right here. That is x is equal to pi over 4. What does tangent equal at this value? Well, tangent, if x is equal to pi over 4, tangent of pi over 4 is the ratio of sine of pi over 4 to cosine of pi over 4. And sine and cosine at pi over 4 equal the same exact thing. It's root 2 over 2 divided by root 2 over 2, which is 1. So I know at pi over 4, tangent is equal to 1, so I get this value here. Well, what about at negative pi over 4? Well, instead of getting a positive 1, we'll get a negative 1. So I'll get this value right here. In between negative pi over 2 and pi over 2, and these 3 points, I'm going to sketch in what the tangent function looks like. It goes through those points, and it approaches the asymptotes. So if I'm going to sketch my graph, I get something that looks like this. And what happens over here and over here? Well, this thing is periodic, meaning this pattern continues forever in both directions. So like over here from pi over 2 to pi, the graph will approach the asymptote like this, and then there is an asymptote over here, it just doesn't fit in my window, but it'll go up like this. So this pattern will continue forever in this direction. And the same thing happens going over here. So the graph will look like this. It will approach the asymptote and drop down like this over here. So from this graph, one thing to note is the period of tangent is pi. And the reason for this is this part here from negative pi over 2 to pi over 2 tells you what the tangent function looks like, and the length from here to here is a distance of pi. So I'll just make note of this. And that is pretty much it for the graph of tangent. So this is the general shape. This is one period of tangent. The period is pi. And then it is copied and pasted forever in both directions. Now, what about the graph of cotangent? So if we want to graph y is equal to cotangent of x, understanding the domain would be a good place to start. And for the definition, I'll use cosine of x divided by sine of x. So cotangent is the reciprocal of tangent. So I'm going to write it like this. I'll take the fraction for tangent and flip it. Anytime that sine of x is equal to 0, those are not going to be values in the domain of this function. So, where does that happen? Sine of x is equal to 0 if x is equal to 0, plus or minus pi, plus or minus 2 pi, and so on. So here, on the grid that I have down here, I can only include 0, pi, and negative pi. So let's put in some vertical asymptotes for these places. So here, 0 is not in the domain, and there is a vertical asymptote there. And the same thing happens at negative pi and positive pi. That's all that will fit in my axes that I have here. So I'll just note that these are vertical asymptotes. If you want to start actually graphing this function and you want some points on it, well, knowing where cosine of x is equal to 0 will be helpful, because that's where cotangent will equal 0. So for that, where is cosine of x equal to 0? Well, that's going to occur at plus or minus pi over 2, plus or minus 3 pi over 2, and so on. So let's see, if I plot those points, let's see, I get negative pi over 2 as well as pi over 2, and that's all that's going to fit on the axes that I have here. So maybe we'll get a couple more points in between here and here to get a general idea of what the graph is going to look like. It has to approach the asymptotes as well as go through this point here. I think a couple of useful points would be, well, what about at x is equal to pi over 4, which is this x value right here? What does cotangent equal here? And since cotangent is the reciprocal of tangent, cotangent of pi over 4 is equal to 1 over tangent of pi over 4. And we know that tangent of pi over 4 is 1 from our previous slide. So at pi over 4, cotangent is equal to 1. If you were to check 3 pi over 4, the only difference is you'll get negative 1 instead of positive 1. So I'll just note that when x is equal to 3 pi over 4, cotangent at this angle is negative 1 instead of positive 1. And so you get this point down here. Between here and here, cotangent has to go through these points and approach these asymptotes. So if I sketch that in, I get something that looks like this. So the graph drops down, it goes between these points, and then it continues towards the asymptote over here. And this is one period of cotangent. This will be copy and pasted forever in both directions. So over here, for example, the graph looks really similar. We get these points. The graph has to approach the asymptotes, and so we get something that looks like this. And like I said, this goes forever in this direction and this direction. I'll note that the period of cotangent is pi, just like tangent. So this is the general shape of the graph. Its period is pi, and here are a few values and some asymptotes. So we looked at the graph of tangent. We looked at its reciprocal, which was cotangent. Since we know the graphs of sine and cosine, they have reciprocals as well. So what about cosecant, which is abbreviated like this? What's the definition of this function? It is the reciprocal of sine of x. So down here on the axes that I have provided, I have the graph of sine already, and I put this here so I can use it as a guide to sketch a graph of cosecant of x. Like, what's that going to look like? And I'm going to start with the domain. For the domain of this function, I don't want sine of x to equal 0. And as we've stated, this occurs at 0, plus or minus pi, plus or minus 2 pi, and so on. And what this means is any place where sine is equal to 0, I can draw in a vertical asymptote. So I'm going to go ahead and do that. So we have a vertical asymptote here, as well as here, at 0, pi, and 2 pi. Okay, so let's note that these are vertical asymptotes. Now, what does the graph look like where it is defined? So not at places like 0, pi, or 2 pi. Like what's happening in between here and here? What does the graph of cosecant of x look like? One thing to note is that wherever sine is equal to 1, 1 over 1 gives you 1, so cosecant is equal to 1 there as well. That occurs at pi over 2. Sine of x is equal to 1 here, therefore so is cosecant. They share a point. So like this spot here, I know that cosecant of x is equal to 1. You probably noticed that it also happens over here. Furthermore, if sine of x is equal to negative 1, 1 over negative 1 is negative 1, so cosecant of x will equal negative 1 there as well. And there's two places where this occurs, that is here and here. If you focus on this point, that's cosecant of x is equal to 1. The graph goes through this point and it has to approach these two vertical asymptotes. If you want to sketch in the entire graph around it, you get something that looks like this. It must approach the asymptote on both sides, as well as go through that value of 1. So from 0 to pi, this is the graph of cosecant. And you get the same exact thing over here. So the graph comes down, it has to go through the value 1, and then it has to approach the vertical asymptote again. This thing can't cross over the x-axis and approach down this way because sine is never negative here. It never actually equals 0. So what happens in between here and here and here and here? Something very similar. The graph has to go through that point at negative 1, but it has to approach both of the vertical asymptotes like this. Again, not like a perfect sketch, but this is the general idea of what the function cosecant of x is doing. So what is the period of this function? The period of cosecant is 2 pi. The same as for sine. You get this piece up here, you get this piece down here, and it's this thing that is copied and pasted forever in both directions. So when graphing cosecant, and the same thing will happen with secant, actually having the graph of sine and cosine as a guide is useful because you can see where the original function is equal to 0. On the reciprocal, there's going to be a vertical asymptote there. You can also see where the function takes on a value of 1 or negative 1. And they have to be equal there as well. The rest can be sketched by having the reciprocal function approach the asymptotes. So finally, let's use this idea with secant. So secant, abbreviated like this, by definition is the reciprocal of cosine. So wherever cosine of x is equal to 0, those values of x cannot be in the domain of secant. Down here, I have a graph of cosine, and I can see the places where it equals 0. Here, 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 and here. So just to state those again, we've done it a couple of times, but the places where cosine of x is equal to 0 is at plus or minus pi over 2, plus or minus 3 pi over 2, 5 pi over 2, 7 pi over 2, and so on. So at these places, I'm going to draw in a vertical asymptote. So there's one here, there's one here, here, and here. So I'll note that these are vertical asymptotes. Next, where is cosine of x equal to 1? Wherever that happens, secant of x must be equal to 1 as well. And I can see there are 1, 2, 3 places where cosine is equal to 1. Therefore, secant must be 1 here, here, and here. Likewise, any place where cosine is equal to -1, secant is going to be equal to -1 as well. There are 2 places where that occurs, at -pi and +pi. So I'll list those like this. The rest of this will look exactly like cosecant. For example, here between -pi/2 and +pi/2, secant has to go through that point and approach these asymptotes. It's never 0 nor negative. It can't be down here. So the graph must look something like this. The same thing happens over here and here. The only difference between here and here is that the graph will be negative instead of positive, and so the picture that you get looks like this. Here's the graph of the function. And just like with cosecant, secant has a period of 2 pi. So I'll just state that as well. The period of secant is 2 pi. So now that we have these basic sketches of those 4 trig functions, let's see if we can identify more complicated ones by using transformations. All right, example 1. Which is the correct graph of y is equal to 6 tangent of x over 6? And here we have to decide between these 3 graphs, which is the correct one. The first thing I'm noticing is that this 6 is positive in front of tangent, meaning this stretches the graph and it does not reflect it. And what I remember about tangent is tangent was increasing, not decreasing like this. So automatically, I'm going to eliminate this one. Like this one's no good. So I'll just put, for the green graph, I'll put no, this can't be it. And the reason for this is this would be more like y is equal to maybe, I don't know, maybe -6 tangent of x over 6. Again, this negative would flip the graph upside down, and this looks a lot like the tangent function, except this one is decreasing instead of increasing. Okay, so now we have 2 choices. The correct graph is either this one or this one, and maybe we can use this x over 6 to help us figure out which is which. Okay, in x over 6, this is changing the x values, and it doesn't divide them by 6. It actually multiplies them by 6. If we change the x's, it'll have the opposite effect. And if I remember, tangent was equal to 0 at 0, so that's true for this graph and for this one. I remember the vertical asymptote of tangent was at pi over 2. So maybe I'll just make note of this. For just tangent of x, there was a vertical asymptote at pi over 2. And here, this divided by 6 is really going to multiply this location, this x value, by 6. So if I take this x value and I multiply it by 6, the value I get is 3 pi. On this function, I'm expecting a vertical asymptote at 3 pi instead of pi over 2 because we changed it from x to x over 6. So between this graph and this graph, well, if this is 5 pi, that's 1, 2. So here's 3 pi. There is definitely no vertical asymptote here on this graph at 3 pi. So I'm going to say for this one, no, this one's no good. I can't really tell. Like maybe the vertical asymptote is, maybe it's here at 2 pi or something like that. All I know is it doesn't match up with this x over 6. So for this reason, the correct graph is this one over here. This must be y is equal to 6 times tangent of x over 6. There's a vertical asymptote at 3 pi, which matches up with this over 6. And the graph also does look stretched, so it's stretched in a positive direction, and that's it. In example 2, I want to identify the correct graph of y is equal to cotangent of x minus pi over 4. Now, this x minus pi over 4 is going to be a shift, and it's going to be a left or right. So this is a horizontal shift of pi over 4 to the right. I'm just going to make a note that, okay, for this graph, it's going right pi over 4. So if I can remember what the graph of cotangent looks like, I can move the entire thing by pi over 4, and that will be the correct graph. Maybe referring to the vertical asymptotes would be a good idea. So if I'm remembering correctly, there are vertical asymptotes at x is equal to 0 and also x is equal to pi. And then the graph of cotangent was decreasing, where cotangent was increasing. So if we move these by pi over 4, I'm expecting vertical asymptotes at x is equal to, well, if you add pi over 4 to 0, you get pi over 4. And if you add pi over 4 to pi, you get 5 pi over 4. So that will be on this graph. And if I look at this equation here, this is the first one I noticed, it kind of looks like cotangent because it's decreasing and there's a vertical asymptote at 0, but there are no vertical asymptotes at pi over 4 or 5 pi over 4. So because of this, I'm going to say no, it's definitely not this one. That can't be the correct graph. Hey, same thing goes for this one here. There is a vertical asymptote, but it's here at pi over, this is pi over 2. So here's pi over 2, and there's definitely, a vertical asymptote there, but that's not what I'm expecting. So for this one, I'm going to say no as well, like that one does not work. Looks like it's going to be the red graph again. If I'm looking at this one, here's pi over 4, and there does appear to be a vertical asymptote. That's at pi over 4. And if I go pi over 4 above pi, looks like I get another one here. So it looks like we got this other one here at 5 pi over 4. So for this reason, this looks like the correct graph. This is y is equal to cotangent of x minus pi over 4. And finally, for example 3, let's identify the correct graph of y is equal to 3 times secant of x. Well, first of all, this 3 is going to stretch the graph. And if I remember, there were places where secant was equal to 1 and negative 1. The difference here is that they'll be at 3 and negative 3. And if I look at all of these graphs, okay, like this value here is at 3, this is at negative 3. That happens here and here. So unfortunately, I really can't use that 3 to help identify the correct graph. So I think I'll try to use some vertical asymptotes again. So if we recall that secant is the reciprocal of cosine, if we want vertical asymptotes, I want to find places where cosine is equal to 0. And that happened at plus or minus pi over 2 and 3 pi over 2 and so on. So if I look at this first graph, there is a vertical asymptote at 0 as well as at pi and negative pi. So I know this first graph cannot be the correct graph. In fact, this looks more like a y is equal to 3 cosecant of x. And the reason for this is you can draw in a 3 sine of x that matches up with the graph nicely. So that's not cosine. Let's see. Okay, for this one, okay, here we have vertical asymptotes at pi over 2 and negative pi over 2, so that's good. But the problem here is this is definitely a reciprocal of a cosine function. So you get something that looks like this. But the problem is that this is y is equal to a negative cosine of x. And that's not what we're looking for here, because the reciprocal would be negative 3 secant of x. Maybe I'll put a 3 here as well. So the problem with this one is the graph is upside down because there's an extra negative in here. So for this reason, no, this one also no good. But if you look at this one here, this appears to be perfect. Here I'm drawing in the graph of y is equal to 3 cosine of x. The reciprocal will give me secant, and so this actually matches up perfectly. So this one here, the green one, yes, this is the correct graph. That is the reciprocal that we are looking for.